Okay, hello, my name is Ryan Bachman, and today I'll be talking to you about our paper, Can Students' Spatial Skills Predict Their Programming Abilities? Introductory computing courses are known to have a high failure rate, and many studies have looked into how it might be possible to predict at-risk students. Among these studies, it has been found that many variables help to predict at-risk students. These include clicker scores, online quizzes, prior programming experiences, and many other factors. However, none of these studies actually looked into how well students' spatial skills might be able to predict their success. So spatial skills is considered to be the ability to use and manipulate spatial information. There are plenty of different kinds of spatial skills, from navigation, map reading, paper folding to mental rotations. These are just a few different spatial skills. And the example that I'm showing you is from the Purdue Spatial Visualization Test Revised. This tests a person's ability to mentally rotate blocks. So given a block and a rotation, can you perform the same rotation and match the correct answer? In the example that I provided, the correct answer should be D. Spatial skills have been shown to be important in success in many STEM fields. Recent studies have found that students' spatial skills have high correlations to students' programming abilities. It was even shown that with the use of a spatial skills intervention that was run alongside an introductory computing course, both students' spatial skills and programming abilities increased. However, these studies have not looked into if students' prior spatial skills are a good indicator at predicting their success in computing. So with that, we wanted to ask the following questions. 1, what is the predictability of each individual variable that we collected at predicting students' post-programming abilities? 2, what variables contribute to a model with the highest overall accuracy? We collected data from 119 students from 3 universities across the US. Data was collected in a pre-post format and used 4 instruments to gauge students' programming abilities, spatial skills, attitudes towards computing, and basic demographics. So the first instrument was the SCS1R. This consisted of 9 questions that was used to gauge students' introductory programming abilities. And the Purdue Spatial Visualization Test was used to gauge students' spatial skills and consisted of 30 questions to gauge students' ability to mentally rotate objects. So the third instrument that we used was the CAS-V4. This consisted of 26 Likert scale questions to gauge students' attitudes towards 5 different factors towards computing. The first factor is problem-solving transfer. It consisted of questions that related to a student's ability to see and or apply connections between concepts and the ideas in order to solve problems. The next factor is personal interest. It consisted of questions related to personal interest, motivation, and engagement with computer science. Problem-solving strategies consisted of questions that focused on classic problem-solving strategies in computer science, including topics of practice, problem decomposition, and planning prior to writing code. So real-world connections consisted of questions that dealt with the relationship between the real world and computer science, and problem-solving fixed mindset consisted of questions that related to students' belief or predetermined fate or learned helplessness with computing. With that, we split students into 3 categories based on how well they performed on the post-programming ability test. These categories included low, middle, and high ability. We used a multinomial logistic regression model to predict students' ability based on their prior variables, so the data that we collected at the beginning of the semester. Data was randomly split in half, so 50% of the data was used to train the model, and the other 50% of the data was used to test the model. We used overall accuracy to measure the performance of the model. Our first question was that we wanted to look at each individual variable to predict student success. In the end, we found that prior spatial skills had the highest predictability, followed by prior programming ability, gender, and problem-solving fixed mindset. I'll give you a second to look over the table. Okay, moving on. So our second question was to find a combination of variables that resulted in a model with the highest overall accuracy. The model that had the highest overall accuracy was achieved by using prior programming abilities, prior spatial skills, socioeconomic status, problem-solving transfer, personal interest, and problem-solving fixed mindset attitude factors. Here we used a confusion matrix to show the model predicted, or how the model predicted each student versus how well each student actually did. So the left column is what the model predicted each student doing, and the top row is how well each student actually did. So the sum of the diagonal will be the total number the model correctly predicted. In this case, it predicted 64.6% of the students correctly. In conclusion, we found that students' prior spatial skills had the highest individual accuracy, and when accounting for prior programming abilities, prior spatial skills, socioeconomic status, problem-solving transfer, personal interest, and problem-solving fixed mindset resulted in a model that had the highest overall accuracy. In the future, we would like to collect more data based on what other studies found to be a good predictor and add those to our model to see if that further improves our overall accuracy. Some of the references that I used in this presentation. And if you have any questions, please email me at ryanbachman@huskers.unl.edu. And yeah, thank you for watching my presentation.